Luke Barnes. We're very happy that he could join us today. I'll just give you a very brief idea. So Dr. Luke Barnes is currently a postdoc researcher at the Sydney Institute for Astronomy, still current, I hope, sort of, at the University of Sydney. He won the University Medal at the University of Sydney and got a scholarship and completed his PhD at Cambridge in the UK. And he's published lots of articles and more than one book, or
No.
just the one book so far, the first one. So this looks like a fascinating book, A Fortunate Universe, Life in a Finely Tuned Cosmos, co-authored with Geraint F. Lewis. He also maintains a blog, which I looked up, which has some fascinating headings. He engages with the thinking and the arguments of people like William Lane Craig and Victor Stenger, and various other people. Lots of really interesting topics, not only about cosmology and those sort of things, but a few other topics are there on the blog you might be interested to have a look at. And one in particular which I found particularly fascinating and of crucial importance. There are a few blogs there on batting in cricket. Fascinating topic, deep scientific underpinnings to a very important part of human society. So I think they're the ones I'm going to read first. They're the most important ones of all. So tonight, Luke is going to be leading us around the topic of the fine-tuning of the universe. Why is the universe so apparently hospitable to things like human beings and stars and those sort of things? So without further ado, I'll hand over to Luke. Thank you very much.
Thank you. Right, thank you very much for coming out. I did some research before I got here. I believe the stuff outside's called rain. It's been a while, but that's what that stuff is. I'm happy at any point to ditch this talk and talk about cricket for the rest of the evening, but while I'm here, we'll get started. So I'm an astronomer by training and by profession. I'm sort of at the University of Sydney. I'm sort of on my way over to Western Sydney University. And so that's the story there. But one of the great things when you are an astronomer is that no one really has to talk you into being an astronomer, because the universe looks like that. No one ever has to sort of sit you down and give you the stern talking to about why you would want to be an astronomer. It's perfectly obvious. You get to stare at that thing for a living. When astronomers get together to talk about careers in astronomy, the main question is, how on earth do we get paid to stare at the universe like that? One of the great things about the universe is that the harder you look at it, the more beautiful it gets. So, for example, there are bits of the universe which are clouds of gas, some of them are collapsing to form stars. They are lit up by stars that are around them, and so they look like this. This is just a regular gas cloud lying around in the universe. Stars burn fuel to light themselves, and when a star runs out of a certain type of fuel, it will try and get hotter and denser to light up a new source of fuel. Maybe it was burning hydrogen, it will start burning helium, and that fuel change looks a bit like this. That's a planetary nebula. You really do owe yourself a good, that screen's pretty good, just to get a dark room and a nice high resolution screen and some Beethoven and a good whiskey, and just really enjoy yourself on the Hubble Space Telescope website. If the star is unable to light a new source of fuel, it will often just collapse and explode. So that's the aftermath of a stellar explosion. And if a whole heap of stars get together and make a family photo, they look like galaxies. So there's actually two galaxies that are sort of in the process of interacting with each other. So no one has to talk you into being an astronomer. No one says, would you like to look at that stuff for a living day in and day out? That all sounds rather good. If, like me, you're a maths nerd, then there is another level of beauty out there in the universe, which it is quite enjoyable to think about. Right? There are laws that govern all of this stuff, the stuff that arranges into this particular arrangement. Okay? What I want to do is give you a very quick run through of what those laws are like. There's no test at the end, so you will be all fine. But we're heading towards a deeper question here, and the deeper question is, why is the universe the way it is? And in particular, what if it had been a bit different? So let me, with that in mind, give you a very brief run-through of the stuff that you're made out of. There's a subfield of physics called particle physics, and their remit, their entire purpose of existing, is to grab stuff in the universe and smash it into itself and try to break it into the smallest bits that they can. That's particle physics. So far, all of the stuff we see around us is made out of three particles, which you'll see on the top left. They're the up quark, the down quark, and the electron. Remember those? They may win you a pub quiz evening at some point in the future. Right, everything, all this stuff, the chairs, the building, all of that, everything we've seen in the universe, which is made out of regular stuff, boils down to those three. Now, we found a few other things in the universe. There's other types of quarks. The electron has a few older brothers, and there's some weird stuff going around called the neutrinos. But all the regular stuff that we're made out of, ordinary matter, boils down to those three. Okay? In short, the Lego set of the universe has only three types of brick in it. What can we make out of those three bricks? Well, there's step one there. You can combine quarks to make protons and neutrons. Right, if you're playing along at home, 2 ups and a down makes a proton, 2 downs and an up makes a neutron. There's step one. Step two, we can put protons and neutrons together to make the middle there, the nuclei of atoms. Protons and neutrons will stick to each other, and in particular, all the different ways that you can stick together a nucleus are just all the elements in the periodic table. I've made the periodic table nice and small there so you don't get flashbacks about high school. But basically, the number of protons you can stick in the middle just gives you which number in the periodic table you are. 1 is hydrogen, 2 is helium, and so on, all the way up to those large ones down the bottom. So we're just sticking stuff together and seeing what we can make. As you can see in the diagram at the top left, if you put an electron around the outside, because the proton is positively charged, it can attract electrons, which are negatively charged. And in particular, as well as going around the outside, if you put nuclei close to each other, the sort of the yellowy things in the bottom right, an electron going around them won't just stick to its own nucleus, it'll take a complicated path around that whole outside there, the sort of Mickey Mouse shape, which will bind things together, and that in 2 sentences is chemistry, right? I mean, they make it so difficult, but that's basically it. That's all there is to chemistry. In practice, the universe does an awful lot with chemistry, like DNA. So if you put those 5 elements, hydrogen, oxygen, nitrogen, carbon, and phosphorus, which in and of themselves are just certain arrangements of protons and neutrons, into that order, you can literally write the instructions for a person or any other form of life that we've ever come across, right? Which is kind of amazing. The rungs that go across the middle of that helix literally encode letters in a code, right? They represent another particle, another type of molecule, that's going to get arranged into a certain arrangement and then to build up things like cells. And we're into biology where I'm way out of my depth, but the short story is that cells are really complicated, which is why I'm happy I'm a physicist. Yeah, every cell in your body has its own postal system. Every cell, not just the body as a whole. If the cell wants to get a certain chemical from one side to another, it doesn't just sort of throw it in that direction or let it loose and hope it turns up. There are little chemical highways with little chemical trucks on them. So what happens is the payload, a little address molecule is stuck on it. It's loaded into a little truck. That truck goes down a highway. The address gets checked, and when it reaches the right address, it gets unloaded and put to work somewhere, right? Every cell of your body is doing that at this moment with whatever you had for lunch. Right? This is how life works. If you stick enough of these cells together, you can actually make small people and larger people. And that's, in a short, very short story, that's life. So in short, with some assembly required, you can turn the basic stuff of our universe into people. Now, that slide there is giving an unreasonable assessment of how easy that process is, right? Better methods are available than that, from building it from quarks and electrons. But that's the short story. So if that was all way too much science too quickly, let me just summarise very briefly. You're made of stuff. When we look at that, one of the wonderful things about being, in particular, an astrophysicist, when you look out at those beautiful things in the universe like galaxies and stars, is that you can take the stuff that we're all made of, which we can see in particle physics experiments, look at how that stuff works and start to understand how the bigger stuff in the universe works. We can break down, say, stars to an understanding of how gravity works, how pressure works, how nuclear reactions work, and we can start to understand what those bright things in the sky are. But this raises for us a question, and the question I want to start sort of moving towards here. With our understanding of how these basic bits of the universe work, and it's all equations, I won't show you any equations, don't worry about that. When we have those equations, we can play what-if games. We can start to wonder about the contingencies of life. One of the reasons why we write fictional stories as a sort of species and have movies is because there's a whole heap of other ways we think that life could have been. If you were watching TV last night, Back to the Future was on. The whole point of time travel movies is, what if we sort of went around and tried this all again? How could things have turned out differently? It's a very basic thing about human life. We wonder about the different ways that life could have turned out. And if we're wondering about why the universe is the way it is, a good place to start is all of these basic bits of the universe to say, what if they'd been different? What if gravity was stronger? We're all familiar with gravity. You're all sitting on the floor. No one is sitting on the roof, on the ceiling, okay? That's gravity. What if gravity was stronger? It has a certain strength to this force. There's a certain amount of energy it takes to lift any of the things around us. What if it was stronger? What if the electron were more massive? What if it had more mass? Okay, what if it was heavier? What if atoms were more stable or less stable? What if there were a different number of dimensions of space and time? This is a fun one because it sounds bonkers. Sounds like you're doing Doctor Who or something, but we can actually write down equations that describe universes in which there are 4 dimensions of space, or 2 dimensions of time. That's a particularly weird one. And we can work out what would be going on. And so the question is, what kind of universe could there have been? What happens if we go messing around with the way the universe is to ask how things could have been different? And the interesting part of this story is, almost all the time, you ruin the universe. So let me give you some examples. Here's our simple picture of how an atom works, right? Proton and neutron stuck together in the middle, electron going around the outside. This is obviously a classical picture. There is thankfully no sign of quantum mechanics here, which is nice. This is called deuterium, by the way. There's 1 proton in there, so it's a type of hydrogen. You stick a neutron in there, and it's deuterium. Let's take some of the basic properties of our universe and change them. So I introduced you before to the Lego set. Remember, that's going to win you that pub quiz, up quark, down quark, electron. Let's take the stuff that's inside those protons and neutrons, up and down quarks, and just make them a bit heavier or a bit lighter. There's a start. Okay? There's a very basic property of a thing is how much it weighs, how much mass is there. What if we changed that? Now, you might think if I do that, all I'll do is make the stuff of the universe either heavier or lighter in total. But actually, that's not how it works. And the reason is Einstein's famous equation. I promise no equations, but I'll get away with E equals mc squared because everyone knows that one anyway, right? Good. Energy is mass is a form of energy. And so nuclear reactions, for example, all that energy that comes out before was in the form of mass. Energy is kind of the currency of the universe when you're a physicist, okay? If something in the universe is going to happen, it needs to have enough energy. If you want some process to happen, you've got to be able to pay for it with energy, and if you don't have enough energy, it doesn't happen. If you start messing around with the basic masses of all the stuff, you start messing with the accountancy of the universe. There's this process where you start with these things and you end up with that thing, and the universe can afford it. But if you start changing how much all these individual pieces cost in terms of energy, you can start to say, okay, that reaction now doesn't work, this one does work, and you're starting to mess with the fundamental stuff that can happen in the universe. And it actually doesn't take too much before the proton and neutron will not stick to each other. The neutron will simply leave. The way, in this analogy, the way you make something stable is you make it broke. If you want proton and neutron to stick to each other, you need that system not to have enough energy to be able to do anything. You just want it to stay there, okay? There's an analogy here with teenagers. Don't give them any money and they won't get into too much trouble, okay? If you want a stable thing, like all of the atoms in your DNA, for example, you'd like those to be the same when you wake up tomorrow morning, make them all broke, or relatively broke, so they won't do anything. There's not enough energy around. If you start messing around, you can make it the case that actually those two things won't stick to each other. They'll have enough energy to break apart. Doesn't take too much other sort of messing around with the basic stuff in the universe before actually you can make it so that electron won't go around the outside. It'll spiral into the nucleus and make a neutron. Here's why all of this matters. Here's that periodic table again. Just for fun, this is the astronomer's periodic table. It's coloured according to where that particular element is made in the universe. So hydrogen and helium are made in the Big Bang, purple ones. All the yellow ones in the sort of top right over there are made in small stars, but if you want to make the bigger ones, the green ones, you're going to need some larger stars which are hotter, right? And then if you want to make those orangey sort of ones, actually a really big hot star isn't enough. You actually need to blow your star up in supernova. So for example, if you see AU there in the middle, that's gold. Gold was made in supernovae. There's your little factoid for the day. There's a row along the bottom there, the purple ones, which even the universe doesn't bother to make. We had to make those ourselves in a lab for no apparent reason, just to see if we could. That's the sort of the menu of the universe. If you want to go do some chemistry and make some interesting stuff like people, here's all the stuff you can make to interact with each other, right? So all the chemical reactions are there. If you mess with these fundamental properties of the universe just a little bit so that protons and neutrons don't stick to each other anymore, the periodic table looks like this, which is great, right? That would be really cheap to put on the, on the wall of every classroom, right? It's just hydrogen, nothing else. If stuff doesn't stick, then you don't get anything else, okay? In that universe, the chemistry exam goes like this. Question 1, what is the element? Hydrogen. Good. We're all on top of that one. Question 2, what is the chemical reaction? Because there's only one. You can put hydrogen together with another hydrogen, that's all there is, and make a hydrogen molecule. And that ends the chemistry exam, because there are no other chemical facts. There's nothing else the universe does. Okay? This fact, okay, that all of that beautiful complexity in our universe, all the complexity of chemistry, right, which makes physicists not want to do it, all of that beautiful chemistry which underlies the interesting stuff the universe does, like people, all of that we can make dissolve and just completely abandon us with a very small change in the basic properties of the universe. Is that me or is that... So this is called the fine-tuning of the universe for life. The picture there is of a radio dial that you are turning. If you want to get that particular frequency, that particular channel that you want, you have to hit a very small range, because if you're too far one way, too far the other way, you might get static or you might get Today FM. But if you want that one that you're after, you've got to be in a very narrow range. If I show that plot to a high schooler, they generally don't know what that is, and I have to kind of explain. Okay, back in the old days, you had to turn a radio dial with your hand. So that's an example. Let me give you another one, one that's a bit closer to the actual research that I do, which is asking how galaxies form. So the way that we study this with a computer, because it's a big, messy, complicated problem, is you make sort of a universe inside a computer within an expanding space. you put particles that represent the stuff in the universe, and then you teach them to interact with each other. You program them to interact with each other. They will attract each other via gravity. They will feel pressure forces when they get close. If a bit of the universe gets particularly dense, then stars will form. At the end of their lives, those stars will blow up into supernovae, which if you see in the bottom left, some things blow up there. That's what's going on. And in particular, because if there's any blob of stuff in the universe, because gravity is always attractive, basically the rich get richer. If there's any dense bit of the universe, it will grab stuff, sort of draw more stuff in via gravity and get even bigger and denser. And that's the short story of how matter forms in our universe. The final picture we have is what's called the cosmic web, where the densest bits of the universe are just sort of grabbing things around us, and there's sort of thin filaments between those dense knots where matter is still trying to decide whether it wants to fall one way or the other. Okay? So that is a picture of the complexity of our universe on a massive scale. How did our universe make structure at all? The first part of that story is all of this. Right? This is how an initially smooth universe, expanding with gravity, forms dense parts of the universe and things like galaxies. Within those galaxies, stars form. Stars make the heavier elements. Those collect into planets. And on planets, interesting stuff like life can happen. So all this beautiful complexity is there in these. We see this sort of coming out in our simulations of how all of this works. And so if you have the sort of mischievous inclination that led us to ruin chemistry a couple of minutes ago, you can take these simulations as well and see what would happen if we started changing the overall properties of the universe. The hero of this story, as I said, was gravity. If there's any sort of little overdensity, its gravity will pull more stuff in to make even bigger things, and so you get a universe full of structure like galaxies. If you have a universe where gravity is too weak, the random motions of things just sort of flying around, it will be enough to break the bond of gravity and no structure will form. Everything's just featureless. The universe is like a sort of hydrogen soup where nothing interesting happens. In particular, you don't get anything dense enough to even form, everything's a gas. You don't get anything dense enough to form like a liquid or a solid. All of those are just way too dense for anything here. In this universe, because it's expanding, pretty soon what happens is as follows. You have isolated protons, and because the universe expands and nothing is holding on to anything else, the protons become surrounded by a whole heap of empty space. What happens in these universes is as follows. Every now and then another proton comes along, bounces off and heads off into empty space for a while. And that's basically the whole of physics. Right? There's a very boring kid's story to be told in this universe called The Lonely Proton. And that's the only story you get to tell in this universe because nothing else ever happens. Right? Anything else would be fiction. You just end up with protons surrounded by completely empty space, and that's the entire history of the universe. And it's remarkably easy to do. Right? You slip the dial of gravity a bit or the cosmological constant a bit, the stuff the universe is made of, and you end up with a phenomenally boring universe. If you slip the dial the other way with gravity, you can ruin the universe in another kind of interesting way. Here is a video of what the sun would look like if you had eyes good enough to see that way. Do not stare at the sun. I have to say that in every talk. If you stare at the sun, you will not see that. You will see a bright spot very briefly and then darkness for an awfully long time. Good. Okay? But if with the right filters, that's what's going on the surface of the sun. So here's what's happening inside of a sun. Here's all the fun of astrophysics. Yeah? There's a sentence you've never heard before. Thanks to our understanding of the way these forces work, we know that inside a star there's gravity pulling the stuff in, and there must be something fighting the force of gravity because the sun is not collapsing into oblivion, okay? And that thing is heat. The pressure due to heat inside a sun fights back against gravity, and if you look at what would a thing look like if it was roughly that big and gravity was being pulled back by heat, forced back by heat, it would look like a star. in fact, it's hot enough in the centre that even though there's heat sort of leaking out in what we call sunlight, there are nuclear reactions at the centre that means that actually that heat will stay fairly constant for an awfully long period of time, which is why the sun keeps coming up. So, we can ruin this story as well. If we make gravity stronger, here's what happens. The star starts to pulse. Rather than these two being in perfect balance, if there's any sort of perturbation to the star, instead of settling back down to where it started from, the whole star kind of overreacts, right? If the star compresses a bit too much, nuclear reactions will fire up, but they'll overcompensate and make it expand too much, and then gravity will pull it back in too far, and after a couple of pulsations, the star will just blow itself apart. You don't have to do too much to gravity before all stars do this. Anything big enough to light up is unfortunately big enough to blow itself apart. So there are universes in which stars just don't work. Okay? The balance we see in our universe isn't available at all. So there's a sort of brief summary of some of the interesting things that are called the fine-tuning of the universe for life. When we do physics in our universe, we see all these wonderful things around us, and we have some idea about how the basic stuff of the universe puts those things together. When we start to mess with the basic properties of the universe, whether just like how much its little Lego blocks weigh, or its overall structure, like how the universe expands, we find alternative histories of the universe in which nothing as interesting as life is going to happen. Okay, this is called the fine-tuning of the universe for life, and it's the subject of the first 6 chapters of this book that I wrote with Geraint Lewis. If any of you, I don't know what your aspirations are in your careers, but if you're thinking of a career in being a super villain, then there are some really wonderful ideas about how to blow up universes in those first 6 chapters. There are some really phenomenally entertaining ways of just totally ruining everything. We wrote the first 7 chapters together. Geraint is a professor at the University of Sydney. He was my honours and masters supervisor and my boss, and we wrote this book together, we write papers together. Geraint is actually an atheist. So the whole story I've been telling so far, and the story in more detail in the first 7 chapters there, is something that a Christian, like myself, and an atheist can get together and write 7 chapters about and basically agree about everything. Right? If you do us the honour of getting onto Book Depository later and ordering yourself a copy, or Kindle or whatever, there is actually one footnote which begins, at this point, our 2 heroic authors fell into disagreement. And we try and sort out what happened there, but we didn't actually agree on what was going on. There's one footnote, but the rest of it, like the physics is all there in physics journals. We basically summarise what's there. There's nothing particularly to disagree on. What happened next was chapter 8, which takes the form of a dialogue, where we try to work out what all of this means. So let me present Geraint's answer. Okay? His answer is that there is a real problem here, something that physics needs to address. And his solution is something called the multiverse, which, for various reasons, has started turning up in comic books. If you can't read that there, that says Infinite Crisis, Fight for the Multiverse. Batman's involved. I don't know why. But this idea of a multiverse is there's not nearly enough in the scientific literature about the multiverse from cosmologists. There's not nearly enough Batman. But, sorry? No? Good. The idea of a multiverse is something that sounds like science fiction, which is why it keeps turning up in science fiction. The idea is quite simply that other bits of the universe have different properties to ours. The laws and constants of physics, the basic properties of stuff, change from one bit to the other. So, in short, there are sort of, if you sort of zoom back on the universe, it might look like sort of bubbles like this, where there's sort of bubbles where in one of those bubbles the electron has a certain mass, and in a different bubble it has a different mass, and it's sort of all existing together. And the idea is quite simple. It's basically the same as the answer to the question, why does anyone win the lottery? Well, because lots of people buy different tickets. That's the answer to why people win the lottery. the existence, thanks to the fine-tuning for the universe for life, the existence of life in our universe looks phenomenally improbable if you just went and picked some basic properties of the universe at random, set some toddler loose on the dials of the universe to pick his own, I'm thinking of my toddler here, well, he's 4, he's got no excuse, to pick his own value of the electron mass and how the universe expands. They'll almost certainly come up with a universe where nothing sticks and nothing forms and no structure happens and nothing interesting happens. The idea here is the existence of life in this universe is very improbable. How do we explain that? Well, maybe there's lots of other universes with lots of different laws of nature. And if you do that, and if you vary things enough, then this combination we have, or some other combination where life can happen, the very rare ones, will turn up somewhere. And the other thing is, of course, no one is there in the other universes, in most of the dead ones, to go, I wonder why there's no life around here, right? No one's sitting there wondering why their universe doesn't support life, because if there's no life there, no one's wondering. That's the idea of the multiverse. There's an awful lot to be said, one way or the other. The picture that sort of emerges from this is that if we could zoom out on the multiverse as a whole, thanks to fine-tuning, most of those universes would be dead. Right? They don't have a periodic table, they don't have any galaxies, all their stars blew up, protons didn't stick to neutrons, all of that. But at just the right intersection, where all the bits of the universe sort of worked together, hey presto, galaxies form and stars form, and they make heavier elements, and they stick together, and they make planets, and some miracle happens, I don't know, and then life forms, not a biologist, and then, hey presto, along come us to wonder about why we see the universe that we see. So that's one option. It looks like a scientific option. I'd argue it is a scientific option, but there's an awful lot of people who would say, you're supposed to be a scientist, what do you think you're doing? Right? It's supposed to be about evidence and empirical evidence and observations and experiments. This is, by definition, a hypothesis in which all the interesting stuff, like the crux of the hypothesis, is a whole heap of universes which we don't have the slightest possibility of ever observing. At which point, what are you doing as a scientist? So there's all sorts of really interesting questions along those lines. We can ask certain questions if a scientist, a cosmologist, comes up with a multiverse scenario, they've got some theory about how this whole thing works. We can ask questions of that theory about whether, are we at least typical in that multiverse? Or we see the sort of universe we would expect if we actually lived in that multiverse. So all of that is kind of available. But that was Geraint's take in chapter 8. So he defends the multiverse there. I defend the idea that we could explain the universe by the existence of an actual fine-tuner. Okay. Now, I'm a scientist, a cosmologist, so thinking about the multiverse is something that I do. It is something I can approach at least semi-scientifically, and been writing papers on that recently, actually. But I think there's an awful lot here that points towards a fine-tuner. Very briefly, just to settle something, that the universe was constructed by a fine-tuner is not what fine-tuning means to a physicist. As a bit of jargon, it just means that of all the possibilities, only a very small fraction do the interesting thing that you're interested in. That's all it means. So think of that dial again. But we can think about the idea that there is a cosmic fine-tuner, and one of the ways I like to think about this is in terms of a game of chess. Okay? Imagine that some chess pieces tried to work out what the rules of chess were. Right? They observe their universe, right? And they see the way all the pieces move, and slowly they start to piece it together. There's a certain type of piece there called the bishop, which only ever moves diagonally, and if they're very clever, they will slowly start to piece together the rules of chess, until one day, a very sort of enterprising, very clever chess piece might actually work out the rules of chess. And in terms of their universe, their science and their physics, the rules of the reality that they know, that would all be over. It would be done. right? You could write down the rules of chess on a blackboard, step back, and all of the physics in their universe would be done. And the question is then, is there anything else that they would need to know? Are they just done with reality, or have we just found a whole heap of pointers to even deeper questions like, why is there a chessboard at all? And in particular, why are we playing chess and not checkers? There are other possible games. So if they want to start asking those questions, and in particular, if there is any answer at all to those questions, they will not find them in the rules of chess. Right? The rules of chess do not tell you why we're not playing checkers. The rules of chess don't tell you why chess exists at all. So I think this is a way that we can approach this problem. If, way off into the future, Albert Einstein's great-great-great-great-great-great-granddaughter, Alberta, I guess, is at a physics conference and she walks up to the blackboard and she writes down a set of equations, and in actual fact, whether we could know this or not is an interesting question, but in actual fact, that would be like the chess rules. She's basically just solved our universe. Right? Our universe would be like a completed crossword puzzle, right? Just done. Right? Nothing left to fill in on that bottom level. There'd be all the wonderful questions about how those laws actually play out. But in terms of like the way, in an analogy to the way that, you know, if you know the rules of chess, you don't necessarily know all the strategies of chess. So, but in actual fact, we could be staring at a blackboard looking at the rules of our universe, physics being done. Would we still have a whole heap of questions? I think the answer is pretty obviously yes. We'd have very similar questions to what the chess pieces would have, like why is there a universe at all to be described by these laws? And why these laws rather than some other set of mathematically possible laws? I think what fine-tuning points us to is an interesting feature of the laws of our universe which is not shared by a whole heap of other possible laws. Our laws do interesting things like permit the existence of life, and in particular life that has positive moral value. Our universe is neither morally sort of trivial, where everyone just gets along perfectly and no moral integrity is needed, or trivially in the other direction, whether you have no hope of ever influencing the way the world works, but sort of interestingly in the middle, where if you want to be a good person, you've better pull your socks up and get on with it. It's not going to come easy. We live in a universe which permits that sort of thing, and actually most of the other ones don't. And the reason why I think this is interesting, because if you look at the other side of the equation there, if you're thinking in terms of a naturalist, if you think that the universe is the only thing that exists, if you think that natural stuff is the only stuff, then when you're staring there at Alberta's blackboard about the ultimate rules of the universe, those are the ultimate principles of reality, and if you have any further questions, then just swallow them and get on with it, because they don't have any answer. Not just we need some more research, but there is no answer there at all. The problem with that is, if you thought naturalism was true, you'd have no reason to expect any particular set of laws rather than some other one. It's a feature of good explanations that they take a huge set of possibilities and whittle them down to the one that actually exists. There's a good analogy here with the game of Guess Who. Are we familiar with the game of Guess Who? Very quickly, the way this works is you choose one of those faces as a card out of the pile, your opponent also picks one, and then via a series of questions you have to try and work out which of those cards your opponent has. Okay? The really good questions are the ones that let you eliminate a whole heap of possibilities. Okay? If you look where the card is, you'll see Robert in the board directly over his head. If you look one to the left, you'll see someone there who has both a moustache and a beard, whose name is Richard. Turns out in the game of Guess Who, at least in this version, which I grew up with, Richard is the only person with a moustache and a beard. So if you ask a question like, does your person have both a moustache and a beard, and they answer yes, then the game is effectively over, because it can only be Richard. Okay? You can fill the details in on what childhood memory I'm bringing back here, some catastrophically lost game of Guess Who, which ended really quickly. The good questions are the ones where you have a whole heap of possibilities and you get to say, okay, it's not any of those, it's this smaller set. So now think about Alberta's blackboard, okay, which has some equations on it which are probably written in a mathematical language we don't even know yet, which is wonderful. And if you think about not just the ones that is the way our universe is, but let's surround that blackboard with a whole heap of other blackboards about the other ways the universe could have been. This is analogous to the chess pieces saying, okay, here's the rules of chess, and there's the rules of checkers and all the other possible games that are around. If you're a naturalist, there's no reason a priori to expect any of these rules rather than any other ones. If you're a theist, if you think there's a God who values certain things above others, like moral goodness, then there is a reason to focus on the subset of these universes which do interesting things like allow moral virtue, moral value in a universe. That is a property that good explanations have of all the ways the universe could have been. The naturalist has no clue by definition, but the theist can say those ones that do something morally valuable, like people, are more likely. And so I think there's a very strong pointer in that direction. Proof is the wrong way to think about it, I'd suggest. But at least the theist, seeing fine-tuning, sees something that fits nicely into the way that they think about the universe. Of course the universe has positive value. That's why a universe exists, for its value. Whereas the naturalist sees something that's very confusing, in which their worldview has no chance of getting a handle on. That's how I think this argument works. Geraint disagrees, so if you want to see us duke that out in chapter 8, then enjoy. I've got about 5 minutes left. Let me finish with a few thoughts about a few things, and then I'll take some questions. I wanted to particularly just look a bit more deeply about how a theist, someone who believes in God, should think about the laws of nature. So let me give an illustration of the direction I want to take this. This is Newton's defining work. Isaac Newton, it is the greatest work in the history of physics. It is called the Principia Mathematica. It is basically, if you learned any of Newton's physics, this is where he first laid it out, F equals ma and forces and all of that. It's all here. This is in fact a copy of a first edition. There were only a couple of hundred of first editions made, and so these are extremely rare and extremely valuable. There is actually one at the University of Sydney, I found out recently. I'm going to try and get over and see that at some point. This particular copy has something even more amazing about it. It's not just a first edition, it's Newton's first edition. That is his handwriting, where he made some notes about stuff he wanted to change if there was ever a second edition. Okay? This one, of course, is in Cambridge, and good luck getting to see that. I would love to, but that seems unlikely. Here's the analogy I want to sort of draw. Where do you see the hand of Newton on this page? On one level, it's there in the handwriting. The very hand of Newton did the little comment there in the margins, right? There is the hand of Newton. But on a deeper level, the whole page is Newton's. There are just two methods of Newton putting his words on that page. On one, he sent it off to a printer, obviously, to set things up nicely and uniformly and reliably. And then there's the ones on the side where his own hand put something in for a certain purpose. But the whole page is Newton. There are not two things on this page. There is not the stuff Newton did and the stuff that the printer did. It's all Newton. Most of it is the stuff that he sent off to the printer to do reliably and uniformly, and then there's the extra special comments on the side, which were put in there for a special purpose. I think there's an analogy here with the way that we view the universe as theists. What you want to avoid at all costs is a picture in which there are two things. There's the stuff that God does and the stuff that science explains. That is a bad idea. Because if you're a theist, God made the whole thing. And what science is doing is explaining the stuff that God did. So there aren't two things. There's one thing, the stuff that God does. Most of that stuff, the vast majority of that stuff, is so rational and so precise and so ordered that we can do physics with it. We can describe it using mathematical equations. And what we find is we see these mathematical equations running underneath the whole thing. And when we look at the mathematical language we need to describe it, we need the most elegant, most beautiful mathematics that mathematicians have come up with. It is kind of amazing how often we sort of let mathematicians do their thing, however mathematicians work, and just look for the most elegant, the most beautiful, the most powerful mathematics they could think up without any thought about whether it applied to the real universe or not. And when they did that, we found a mathematical language which was then written into the actual universe that we see. Einstein's ideas about gravity are a great example. A whole heap of mathematicians in the 19th century were just thinking about ways that things can curve and the way surfaces work and the way curvature works, and they did a whole heap of wonderful stuff without the slightest caring about whether it actually applied to the real universe. And then Einstein came along and said, I think that gravity is actually the curvature of space-time. What do you know? All of that mathematics is available to me because some people in the 19th century worked an awful lot of it out. That is the picture we get from physics. There are not two things. There is not the stuff that God does and the stuff that science explains. The reason why we need to get rid of that particular idea is because it gives the naturalist, the atheist, the idea that whenever science explains something, they get to reach over and pull something out of the God pile, right? And unfortunately, a lot of Christians kind of fell for this, and so what they need to do is go and grab stuff out of the science pile and say, hey, science doesn't explain everything, right? Who cares if science does explain everything, okay? If science wants to find more order, more beautiful mathematical order in the universe, then let it, right? It's like finding a deeper, more sophisticated summary of the rules of chess. You don't thereby replace the chess player or the person who designed the chessboard. In fact, I like to think of this as, suppose you were watching a great artist put together a mosaic, right? A huge picture is coming together piece by small bits of tiling, okay? If you watch closely enough, and if you're careful enough, you might work out what the picture is, and at some point someone yells out, hey, it's a turtle. At the point at which someone points out, hey, it looks like a turtle, the artist does not disappear. If you describe the pattern of God's works, right, God does not suddenly disappear. When science describes the universe, it describes the stuff that God did. I like this quote from a great physicist from around the same time as Einstein, actually, Poincaré, who said, we shouldn't be astonished by nature's regularity. Men demand of their gods to prove their existence by miracles, but the eternal marvel is that there are not miracles without cease. The world is divine because it is a harmony. I think once you've got a handle on this, there's it answers a very old objection, which is put quite nicely here by JBS Haldane, who was an atheist and a biologist. Here's his quote. This one still pops up from time to time, but he said, my practice as a scientist is atheistic. That is to say, when I set up an experiment, I assume that no god, angel or devil is going to interfere with its course. The assumption has been justified by such success as I have achieved in my professional career. I should therefore be intellectually dishonest if I were not also atheistic in the affairs of the world. The problem with this is, again, this two-picture thing. There's the stuff that God does and the stuff that science explains. If God does something, it must ruin science. The idea that what science describes is what God does is obviously something that hasn't particularly occurred to JBS Haldane. The picture of God you get out of this quote is one who has nothing better to do than just to ruin some lab technician's day by messing with her experiment. That is not the picture that we have from God. If God is going to actually do something in nature, there will be a good reason for it. Okay? If Newton is going to take his copy of the Principia and write something in the margin, he would have a good reason for it. I want to suggest that there's some, if there is the sort of interference, it would not be as arbitrary and designed to just sort of ruin the day of the scientist. There would be some deeper reason for it. Why is that? Why is it overall that for the theist there are these laws of nature? given that they are not the fundamental thing, they serve some other purpose, here's one reason why we could think why the universe we see around us usually obeys laws, as Haldane says. This is pointed out by Richard Swinburne in his book, The Existence of God. What he points out is that if you're going to make a morally meaningful decision, you need to know what the consequences of your action will be. You can choose to pick up bricks and build a house, or you can choose to pick up explosives and build a bomb, only if bricks and explosives have regular, repeatable properties. If you don't know what bricks and explosives are going to do tomorrow, you don't know whether your action is a good one or a bad one. You might try and blow someone up and end up building them a lovely villa. You might try and build someone a lovely villa and end up blowing them sky high. Why do we see a universe in which there is regular laws? It's because those laws are not the final reason for things, right? We live in a universe in which moral decisions make sense, and so there needs to be consequences, regular consequences of our actions. Given that fact, and it's a fairly basic sort of a consideration, we would expect to see a universe which was roughly scientific, in which you could look at it and see regular patterns. If there was a break in those patterns, they would have to serve some deeper picture. Okay? It's here, there, where I think in particular Christianity has an interesting story to tell. The miracles we see in the life of Jesus of Nazareth are not the kind of random, let's screw with the lab technician kind of miracles. They are, in a very broad way, either looking back to the creation or looking forward to the future creation, to the future. In particular, the sort of the grand miracle, the resurrection, is not God messing with some biology textbooks. It is, in a very literal sense, the turning point of history. Right? There's a wonderful essay called The Grand Miracle by C.S. Lewis, which I will be plagiarising for the last 2 minutes here. He imagines, as an analogy, the picture of a diver who sort of strips off their outer clothes down to their swimmers, dives down into the water, through the clear water down into very deep, dark and murky water, and then pushes back up towards the surface, grabbing with them the thing they went down to get. Okay? In the picture we have of the way the world is working, that turning point is the resurrection. It's the point at which God says, these things in the universe which are temporary, pain and suffering, this is his proof that they are temporary, that they will not be there forever. The reason why God upsets the order in this universe is because one day God will put the order in this universe right. It is in microcosm the hope we have for the future. Right? There is a part of this universe which is temporary. Pain and suffering, there will come a time when this universe is rescued from the bottom and lifted up into the light. So I think thinking through not just the laws of nature, but miracles, I think there is a bigger picture there where the Christian can incorporate both of those. And with that, I think I'll leave it there. If you're interested in more thoughts about fine-tuning, there's the book, also available on audiobook, which was a whole heap of effort, so please buy that. Thank you very much for listening.